Okay, so this is problem 5 from our series of 7 optimization problems. And in this question, we're asked to find the area of the largest rectangle that can be inscribed in a semicircle of radius r. So I've taken the liberty of already drawing a semicircle in blue, and I've inscribed a rectangle in red inside of it. The blue semicircle is restricted by the size of the radius, which we're going to call the parameter r. But the red rectangle can get larger or smaller depending on where we move it within the semicircle. And our job is to try and find the dimensions of the rectangle that'll make it as large as possible. So I guess the first thing we need to do here is we need to identify what the radius of this semicircle is. Now we could label this radius from here out to the outside of the circle, but it would make more sense to label it here from the center to the outside of the semicircle this way, because that allows us to use our radius to define both the semicircle and also to define part of the rectangle. So now I know that my radius is here. Excuse me. Is here. And so we can start our problem. What we want to do here is we want to maximize the area of the rectangle. So we start off with maximize area, and that's followed immediately by area equals. So I need a formula for the area of a rectangle, and of course I know the area of a rectangle is length times width. And that means I now have to go back into my diagram and I have to define a length and a width for my shape. So I'm going to call this the length, and I'm going to label the width up here. And so now I've got both variables defined in my diagram. Now the problem is I have a formula for area in terms of length and width, but I need that formula in area to be in terms of a single unknown. In other words, I need a way to connect L and W. And if I look at my picture, I see a couple of possibilities, but Pythagoras kind of looks like the best one. I can see, for example, that this leg of this triangle is going to be 1/2 of L, and of course this is going to be W. And that gives me, very nicely, that L over 2 quantity squared plus W squared needs to equal R squared. So if I simplify this up a little bit, I now get L squared over 4 plus W squared equals R squared. I don't really love that I've got a fraction in this, and so I might multiply the whole thing through by 4. And I'm going to get L squared plus 4W squared equals 4R squared. And I can simplify this up to L squared equals 4 times R squared minus W squared. That allows me to simplify for L. And I now get L equals plus or minus the square root of this whole thing, which is going to be 2 times the square root of R squared minus W squared. And I can substitute that back into my value for L right there. So my area formula now becomes A equals 2 times the square root of R squared minus W squared times W. I have to account for the fact that there is a plus and a minus root back here where we calculated L, but we can eliminate this negative root and say that this is extraneous because we know that the length of the rectangle needs to be a positive number. We know that anything coming out of the square root is going to be positive, and so 2 times that is also going to be positive, but negative 2 times that would make it negative, and that's extraneous. So we're left with area equals 2 times the square root of R squared minus W squared times W. I can probably make this a little bit friendlier to differentiate by writing it like this, 2W times the square root of R squared minus W squared. And now I have a formula in terms of one unknown. It actually looks like it's still in terms of 2 unknowns, but we have to remember, and this is very important, that R is not an unknown. R is not a variable in this equation. R is a parameter. R is a restriction the semicircle can only be as big as r. R is a constant. We don't know what it is. We're just giving it the variable r, or sorry, the parameter r. But it's a parameter. It's not a variable. It's sort of like in the equation of a line y equals mx plus b. We know that m is a parameter. Okay, m is not a variable. X and y are variables. M is a parameter. It's a constant that just hasn't been defined yet. So the next thing to do here is to decide what is the domain of my equation, the domain of the area. And the domain, well, my variable is w. And so I ask myself, what can w be? What values can w take on? I go back up and I look at my diagram, and I can see that w can get smaller and smaller and smaller as the rectangle gets wider down to 0. W can't be 0 because if it was, we would no longer have a rectangle. So w has to be greater than 0. And likewise, as my rectangle gets skinnier and skinnier and skinnier, that rectangle will get closer and closer to the top of the semicircle, and so my width will get closer and closer to r. Again, w can never equal r because if it did, I would have no width and I would have no semicircle. So w is constrained by from 0 to r, exclusive. You can't have either endpoint. Now that we've done that, we can go ahead and we can take the derivative of this. So I'm going to do that on the next page. So my function that I was working with was a equals 2w times the square root of r squared minus w squared. That's what we had previously. So now I differentiate this, and I differentiate with respect to w, and I see that this is a product rule. So I can sort of imagine breaking this right there, and I have a u and a v. And so I have u prime, which is going to be 2 times v, which is the square root of r squared minus w squared, plus u, which is 2w, times the derivative of the second expression here of the square root of r squared minus w squared. This is of the form root box, and the derivative of root box, of course, is 1 over 2 root box d box. So this is going to be times 1 over 2 times the square root of r squared minus w squared times the derivative of what's inside that radical. And in that radical, I have a negative 2w coming out. Okay, so I can clean this up, and I'm going to be left with 2 times the square root of r squared minus w squared. And here I can see these 2's cancel. I got a minus coming out to the front, so I'm going to have negative, and I'm going to have a w squared, a negative 2w squared over the square root of r squared minus w squared. I believe that's right. Now I need to look for my critical values of this. So I want to know, well, where is this derivative going to fail to exist? And where is this derivative going to equal 0? I'm going to start with where this can not exist. And I'm going to look at this and I'm going to say, well, the only way that I could have this not existing is if either w is bigger than r, which is impossible because that's not in the domain, or if w equals r, that would make this denominator 0. But again, w equals r is not in the domain. According to our domain, w has to be smaller than r, and so therefore, we don't have any issues with this derivative at all. This derivative is going to exist everywhere. And so we're going to say, well, a prime exists for all values of w in the domain for area. And so now we can move on to finding out where a prime equals 0. And if I want a prime equals 0, I can see that I want this entire expression up here to be equal 0, which is the same as saying that the left side equals the right side. So what I've effectively got here is this. 2 times the square root of r squared minus w squared equaling 2w squared over the square root of r squared minus w squared. Now if I multiply the square root over, I can see that I can divide both sides by 2, and that's going to eliminate the 2's. And I'm going to be left with here r squared minus w squared on the left-hand side, and that's going to equal w squared on the right-hand side. And so this works out very nicely to r squared equals 2w squared, and therefore solving for w, because w is the variable I'm interested in, I really get w equals plus or minus the square root of r squared over 2, which is the same as plus or minus the square root of r squared, which is r, divided by root 2. Again, w can't be negative, so that's extraneous. And so I'm left with w equals r over the square root of 2. Now I can set up my labeled sign chart. And so my labeled sign chart is going to have, I've only got one critical value, so I'm only going to have one vertical bar. As always, I'm going to have two horizontal bars. My vertical bar is going to be my critical value, which is w equals r over the square root of 2. And of course, I want a vertical line at A prime, a vertical line at A. Now, I could put values into this and see whether A prime is positive or negative on either side of this, but I can sort of logic this out already. I know that w is allowed to go to the left of r over 2 all the way back to 0, and as it gets closer and closer to 0, a width of 0 gives me an area of 0. And I know that there are rectangles bigger than that. So I know that therefore, this cannot be a minimum because it's going to be smaller over here. So I know that this is getting bigger as we move into it. So I know that this must be a positive because I know that this must be going up. Likewise, going to the other side, my width can go over as big as r. But if my width is r, then my height is 0, and that will also give me an area of 0. So I know that this area is decreasing going this way, so that must have been a minus. And so this must therefore be a local maximum. If you're uncomfortable with that, you can certainly plug values in and you'll determine the same thing. You'll find out that the positive and the negative is exactly as we expected. So now we can write our answer and we can say, well, therefore, area has, and we're looking for an absolute maximum, and we have enough justification up here in the labeled sign chart to get that. So we can say area has an absolute maximum when w equals r over the square root of 2. And the reason for that is because we know that A prime is positive, which means A is increasing, not just to the left of w equals r over 2, but everywhere to the left of w equals r over 2. In other words, on my whole domain, from 0 to r over the square root of 2. And likewise, A prime is negative, which means that A is decreasing on the entire interval from r over the square root of 2 out as far as we can go, which is r in our domain. So now we know what value of w gives us our maximum. Now all we need, because we need the actual area, so we need a value for L. And we know from previously our equation for L was L equals the square root, actually 2 times the square root of r squared minus w squared. And so now plugging in, this is going to be 2 times the square root of r squared minus, and this is r over radical 2 squared, which is going to come out to 2 times the square root of r squared minus r squared over 2, which is 2 times the square root of r squared over 2, and that's going to be 2r over root 2, which is the same as root 2 times r. So we're finished with that, and now we just have to find our final area, our final formula, and it's going to be, area is length times width, and the length we already said is radical 2 times r, and the width we already said is r over radical 2, and that cancels very nicely, and we're just left with an area of r squared. So therefore, the maximum area is r squared. I hope that makes sense. If you have any questions, then feel free to drop by and see me, or send me an email, and I'll do my best to explain. Good luck.